because these things is, sorry. Sorry. በሁለቱም ወደፊት ነው የሚያስኬደው። በሁለቱ በሁለቱም ወደፊት ነው የሚያስኬደው። Now it works. It works, please. Now it works. You see? You see? So, as I told you earlier, all the three classes, the orange, the banana and the apple are merged into one class. So we have made class size reduction. So if these three fruits are merged into one class, rotten or fresh, there should be some way for the proposed detection method to identify the kind of fruit. For that, as you can see, there is some kind of shape information over the fruit, that is shaping for the extraction of shape. We use contour method to extract the shapes so that it is simple for the upcoming model to identify which kind of fruit it is, because we have merged all those things. And this is the result obtained. This one is the experimental setup. This one is the result obtained. This regardless on performance. Later slide will show you about size and response time. As you can see, mobile net, the best mobile net, we have experimented with different byte sizes, and mobile net score 81.16 recall, and DenseNet 85.53, and exception 79.14. So the performance regarding recall, DenseNet, the medium sized model, whose size is 40 megabyte, scores the highest recall. That means if you use this model, most probably, not 100%, or 85% of the time, you will not get, you will not eat spoiled food in this case. This is regarding performance. So the other one is we compare our result with two baselines that use only image data, Han et al. And Mishra. This one use a different data set. Around our data set contains around 10,000 images. This one uses 40,000 images, and it fine tunes using 40 epochs. This one we use the same data set, and the validation accuracy obtained is 95.82%. Ours score BaseNet for 92.39%. The previous one is on recall. This one is on accuracy to compare with the baselines. You see? So our work is somewhat competitive, especially with this one. It is competitive, but it remains a lot to do because it has smaller accuracy due to smaller models and class merge for generalizability. We have made class merge and we have used small models. So the other metric is, all metrics are displayed here regarding size, performance, and the speed. As you can see, regarding size, our post-quantization, the post-quantization module reduced the mobile net from 24 into 3.6 megabyte. But there is no that much punishment on performance, and the other one is DenseNet reduced from 40 into from 20 into 8 megabyte, and the same for exception. So regarding the three metrics, if we want to prioritize performance, we should use DenseNet. If we prioritize model size, or we should use MobileNet. That is the trade-off we solved there. So this is a very important slide. So we reject exception because we didn't get any benefit regarding model size and accuracy in both ways. By the way, response time is originally acceptable, 1 second. Anyone that uses the mobile application can stay for 1 second. Originally it is acceptable, but as a report, MobileNet makes 35 times faster. Originally it was acceptable. It was around 1 second. So we have made significant reduction in size and response time, and significant effect on performance. So we have made also an ablation study, because we suspect that the pre-processing approach that we have made may wrongly mislead the model to detect fresh fruits as rotten because of the artifacts created on the fruits. And our ablation study shows that the hypothesis that I have told you is rejected. Rather, the pre-processing method that we have applied have advantage even, not mislead the model. This is an ablation study that we have made. In all of the cases, once the pre-processing is applied, the performance will be improved. So our hypothesis that says that our pre-processing method create artifacts that mislead the model is rejected. So pre-processing is important. That is an ablation study that we have made. So this is deployment module. This is the deployment module. We have different alert status. You upload the image, and you click on predict, and you get the result. And this is for banana, orange, and apple, all those things, you see? All those things. So in addition, you have different alert status. If the alert status is very high, that means you are very serious about accuracy. You prefer not to eat in high alert status. You prefer not to eat. But if you tolerate, or if you have some kind of alternative method to handle, and if you want this method for cross-checking, you can reduce the alert status. You can with different alert status. So this is the sample GUI. And one thing that I want to tell you is that the accuracy is not yet enough for deployment. Not yet enough. Because we need a very high accurate model. This is a research problem, by the way. You need a very accurate model. You will not resist wrong results. And at the same time, you need a small and high response models. So this thing is unique to this problem. And this can be addressed in future researches. So this is for formality. And we will not deploy this for public consumption. It is not yet accurate. And as a conclusion, this study detects fruit spoilage from the perspective of end user using a 5-module architecture, and the end user has 3 conflicting requirements, have a low-spec smartphone, and the obtained result is competitive, even though it is not yet matured enough. And the future works are listed here, but the main future work that I have identified for your future work, anyone interested in this, is this one. You see? In this research, we handle spoilage. But spoilage can be easily identified by naked eye. Because in spoilage, the fruit is already spoiled in an identifiable way. but contamination is difficult. This is the best. This is the best. End customer may by himself or herself can identify spoilage, but contamination is not identified by our eye. If the mobile application can identify contamination, which is difficult by the end user, this research will be complete, and if the accuracy is increased and the response time and model size is reduced, this will be a very fine work. And these are a very, it opens a research problem for you. As I told you, previous researches, they model only accuracy using image and other IoT devices. These are references, and thank you.
Thank you for your well-organized presentation. So let me summarize the salient features of the work, and I'll give the floor to a Q&A session. Befqadu emphasized on importance of food safety, highlighting critical role, and particularly for identifying spoilage in foods, and mainly the focus was on end users by being able to do the identification on edge devices, typically smartphones. But he also highlighted this research had some conflicting requirements in terms of precision, being a lightweight computational requirement, and it has to be very responsive in terms of latency of processing. Their proposed solution included pre-processing of images, fine-tuning and size reduction, quantization and time management. So as indicated, the performance metrics typically focusing on recall indicated competitive performance with prior works, and also there was an interesting prototype development with a good graphical user interface. So you all had the details. So before coming to my comments and questions, let me report to the audience for the Q&A session. We have about 10 minutes, so feel free to ask or comment.
Okay. My first question is, who is this for? I mean, I don't remember. So, who is this for in particular? I mean, when I think about this kind of tech, it may be more suitable for example, in a factory. For example, in a tomato factory, in a ketchup factory, if two sets of rotten tomatoes get into the processing, it can spoil the whole batch, and this can be disastrous. Your system can help in this kind of situation, but for the consumer end, I don't know who this is for. I don't remember the last time I saw a fruit and questioned if it was spoiled. You can figure that out easily. The other thing is, you said this is for low-spec devices, but the problem with that is not the RAM and the processing. It's the camera. The camera quality can vary vastly from different sets of devices, especially the low-spec devices. They rely heavily on the natural environment. For example, if there is less light, the image quality might be very, very harsh. That can affect the processing. That's my question, and I want to appreciate your work to balance the performance on these low-spec devices? Thank you.
Okay, thank you for your question. The first one is, your question is, it is better to implement these things in factory. Yes, some of the workers that I have shown you, they focus on factory. But it is not only factory that needs these things. You see, end customers also need these things. You see, we need these things. As I told you earlier, it may be easily identifiable for now. But in future, when contamination is also augmented, it will be a good application. And there are also some elderly person and other individuals in the customers who want these things to help their decision. So yes, I agree with you. It is good. But if it were for factory, these three conflicting requirements will not be necessary, because the factory can buy a high-spec machine for that. For a factory, a performance may be important, but model size and response time may not be that much important. Equivalent with these three requirements are important for an end user rather than a factory, because a factory has too much budget. But the end customers with low spec devices, especially those individuals who eat spoiled food, most probably use low spec devices. Do you agree with this correlation? Most individuals who consumes spoiled fruits, mostly they have the low spec mobile phone because of budget. You see? So the other one is, I agree with you. That one is, I captured it, your comment, the camera, because I didn't consider that previously. But if I consider the camera problem of low spec devices, I can deliberately add noise on the original image before training, so that during deployment, the detection will be simple. And thank you for that. Thank you for that, for the camera.
Apologies, the organizers are telling us we need to break the session now, because the other sessions are also going to different meetings. But I want to reflect on a couple of points here for some of you. You have the time to network with Sufkat and you can ask your questions outside. But I want to reflect on a couple of points that you mentioned, especially on your slide 4, and when you were trying to answer this question, you mentioned that people who tend to use or consume spoiled foods tend to have low spec cameras. I think this correlation is quite wrong, and people do not consume spoiled foods by choice. So these premises have been reflected on your slide 4 as well. I think
let me tell you, if a person is there a high-rank restaurant and low-rated restaurant, that means if a person in a high-rank restaurant, usually the foods are quality. But in low-rank restaurant, the management and the control is poor, so your income is low. It shows it relates with income.
The way I look at your solution is in a rather different angle, because with the advent of AI and the computational power of edge devices, and we are also moving into the area of IoTs. It's not about consuming food at the restaurants or anywhere. You can use your edge devices to scan these things wherever you are putting. So that correlation doesn't sound right, because people do not tend to buy spoiled foods by choice. But technically speaking, I would like to give a couple of comments as well, because based on also the comment here, the lighting with respect to taking the image is crucial for image processing on edge devices. So please consider that. And the other one is, while you are using data augmentation to address class imbalances, the model tends to visual operating running devices. So please consider these things in your research. Finally, I would like to ask or comment on the effect of quantization on the model performance, because while you are quantizing activity labels, you have to also change the batch size and